Okay, so welcome to lecture 7 of our CS2 classes. And in yesterday's lecture, we started off with reinsurance. Can someone remind me of what are the types of reinsurance and their subtypes? Anyone? Who would like to talk about proportional reinsurance? Hello. No one? And it's there on the board. You can just summarize it in one line. What's proportional reinsurance and what is... Let's just start off with what is proportional reinsurance. Anyone? Literally, no one wants to try.
Ma'am, in proportional, certain part of claim is paid by the insurance company and the remaining part is paid by the reinsurance company.
Okay. How many guys agree with what just Sauri said? Or is there anything else to add to it? Sauri, that was the correct answer anyways. Thank you very much. So again, whenever we are talking about proportional reinsurance, specifically, we know that a part of the claim is being paid by the reinsurance in any of the reinsurance types. So if I'm specifically asking about what happens in proportional reinsurance, what one should expect to be, summarizing it like is something, there is a certain proportion of the actual gross claim amount that the insurance company pays or the ceding company pays, and the rest of the amount is paid by the reinsurance company. Would someone want to go on about what is non-proportional reinsurance? Anyone?
In non-proportional reinsurance, the company sets up some retention limit. So the claim amount above that retention limit is paid by the reinsurance company, and all the claims below that is paid by the insurance company.
Right. So that's again, so you said the retention limit is set by whom?
Insurance company, right?
Okay, so actually, yeah, it's with the mutual understanding. So I guess you don't have to be that specific as well, but yeah, it's good. So yeah, again, you never know who is there, and it has to be mutually agreed upon retention limit. And I guess we discussed, yes. So we discussed about the moments of proportional reinsurance treaty as well. And again, I think I didn't mention this in the previous lecture, but this C right here has a particular name. Would anyone want to guess what that is? So it's just called retained retention parameter. So this is in actual terms actually known as retention proportion. So again, we have to stress on the word proportion. And with the, so in your books, they would be calling it retention proportion for even proportional as well as non-proportional. But how I like to go about it is that this is retention proportion for proportional reinsurance and retention portion. So, I mean, there's no C in there in the non-proportional. So, it's just the portion that the insurance company pays. So, again, we look at the expectation and the variance in case of proportional. So let's see what happens in case of non-proportional. Did anyone try what happens in non-proportional? Okay, so let us summarize first all that there is to the non-proportional reinsurance. So we have X, the total claim amount, and then we have Y, and let us say the retention limit is M. So we'll have something like this and something like this. And then again, we have something like Z. And for it, again, we'll have some particular distribution. Would anyone want to fill in the blanks for me here? Who will help me with the Y case? So if my claim amount is less than the retention limit, how much is the ceding company going to pay?
So Y will have to pay X.
Yeah. And if it is higher than the retention limit?
Still X.
Still X. Does everyone agree with what
X minus M, I guess.
No, it will have to pay M.
M.
How
It
come
will
M?
be M, right? So it will be X minus M for the reinsurance company. And here it will just be 0. So now let us try to see the expectation and variance in this case. So I guess it's very easy. So let us see that, expectation of X will be what? It will be just integration of X, f of X, dx. All right. So now what will be our expectation of Y?
It was C into expectation of X.
Oh, so that was the case of proportional reinsurance. So when I was talking about proportional,
Right.
yeah, this was my distribution for Y and Z. So I had a similar thing going on for the expectation and variance. But today we're looking at the non-proportional case. So what do you think is going to happen here?
First, it will be integration of 0 to M x f of x dx.
So it will be integration of 0 to M x f of x dx.
Plus integration M to infinity M into f of x dx.
Mihir, can you explain us why did you describe it in such a manner?
In the first case, the x is less than M, so the upper limit is M, and the claim will be always be greater than 0. So first is 0 to M, and in the second case it is x greater than M, so M to M till infinity, and the claim amounts for that range are given x and M, so that's why we multiply it with f of x.
Is this clear? So again, whenever we are trying to take expectation, what do we normally do? We take all the values that X will take and we multiply it with X, which is the value that is going to vary every time, with the PDF, which is just the probability that this particular thing will be observed, and we multiply it with the change in X that we want to sum over and across. So again, for the expectation of Y, what we are doing is we see that our Y value, Y takes two particular values in general, and then there are different values that this X can take depending on what the actual X value is, the actual claim amount is. But we know that Y is going to be M for sure for each claim amount which is higher than the M, which is the retention level. So I know for sure that if I have my integration divided up in two parts, let's say from 0 to M and then M to infinity, so I can have a M here specifically because that is going to be, stable and constant every single time along with f of x and dx. So even if my y is x plus 2, x plus 1000 or x plus 2000, it is, sorry, m plus 2, m plus 2000, it is always going to be m for the seeding company. And then here it is as usual. And we know that this only happens in the case of 0 to m. And this can happen forever, at least in theory, it goes on till infinity. So that's it. And again, we know that, this is just constant. So we can take it outside. So I'll write this as xf of x dx plus, and I'll take this m outside because this variable that we are varying here is x, and m does not depend on x, neither it varies with x. So m can be taken outside, and all we are left with is m till infinity f of x dx. Now, what do you think this can be summarized as? I can write this as this, right? Probability that my x random variable takes a value greater than small m, and this small m is the same small m that I have here. And this is the capital M that I have taken outside. The same. Does this make sense to everyone?
Yes.
Yes.
Okay. So now let us try to see what happens with y expectation of y square. So let's say if I have expectation of y square, what do you think it will be? I don't want Mihir to speak up now. Anyone else? How should I write my expectation of y square?
So will it be the same thing with just x square and m square?
Yeah, so can you dictate?
So it will be integral 0 to m x square into f of x dx plus m square into integral m to infinity f of x dx.
Does everyone understand what I just wrote on the board? And where Vanshita?
Yes, ma'am.
Okay. And the variance would be what? So again, I can just write this as well as the probability that my x takes a value greater than m. So not much in there. Again. So that's there. And then we know for variance of y, it is just going to be expectation of y square minus expectation of y, the whole square. And let us now try to see what happens with the MGF. So if I were to write my moment generating function for y, what will happen? What should be my first step?
Expectation of e raised to yt.
Exactly. And then what should I be doing next?
Integration of e raised to ty into f of x dx.
Integration of
E raised to ty f of x dx.
So I can take this outside.
Yeah.
E raised to ty should come outside. And what should be my limits?
Zero to infinity, right?
Okay, what does everyone agree with what I have just written here?
I didn't get it.
Even I didn't get it. Why are
It will be f of y dy, right, ma'am?
Why are we doing exactly?
Yeah, it should be f of y dy, right?
Yes, ma'am.
And do we know f of y? So again, so remember when I was trying to explain you guys the MGF, what did I say? I said that y is a random variable. So the same way I take expectation of y square, this y square is just a transformation on y, and I'm just squaring it, y. I'm just squaring the y right here. So it is again a transformation on y, and y square is now the new random variable that I'm looking at. So again here, when I have y, and when I do a transformation like e raised to ty, again I'm just making it a new random variable in itself, but instead it is just another transformation on y. So what do you think now? I can write this expectation as think of it just as some another transformation like y square.
It would be integration 0 to m e raised to ty into f of x dx plus integration m to infinity e raised to ty f of x dx.
Is that what you say, Vanshika? Have I written exactly what you said?
No, it would be e raised to tx and e raised to tm.
Right? It should be tx and tm.
Yes.
Because we know when we are when our claim amount is between 0 and m, it's x, and on the other time, and all the other times it's y. Sorry, it's m. So we'll have a m here. So again, these x and that m do come from so this x is exactly from there, and the m that we have is also M went away. M went for a walk. Okay, so I hope that's clear. And we don't actually, need this because we don't know much about the way our f of y is distributed. And instead we can just use f of x and all the values that this takes. So again, I hope that's clear, and that is all that we need to know about these distributions. But again, now what happens next is you can, okay, so again, we can do the same thing from the reinsurer's point of view. We can figure out its mean, its variance, and its moment generating function as well. So whenever we are going to do that, there are two things that can happen with a reinsurer. Either they will have information about all the claims from the past or something else. So this is the time to remember the case study that we did in the first lecture. It was about longevity study of Lombard, right? Does anyone remember what was the crux of that story? Like, why was his study a false study and not, something reliable? So to remind you, it was about, listing down professions alongside with the average longevity for each one of them. So do you guys remember what was the anomaly in there? Anyone?
Ma'am, can you repeat the question, please?
Yeah. So what I said was, remember the case study we did in the very first lecture, not the orientation, the first lecture? It was about Lombard. So this guy studied the professions and the average longevity that each person, let's say, from that profession goes on to live for. And we discussed that, I guess. So there was some anomaly in that, and I did discuss, why was that study not really studying what it wanted to study. It was something about the average longevity of students. Does it ring a bell?
The students one was something about like the age group where he considered that 0 to 80 and something maximum of the people who died were students.
Okay. Not quite exactly, but I see. What about others?
Ma'am, the data selected wasn't quite specific.
What do you mean by quite specific?
Ma'am, like for that student's example, he had considered, like, as far as I remember, he considered all the ages, not only for like if so for the student's case, he hadn't taken all the cases, not only till student's life. Like for example, he should have been taken only till age 25, but he didn't do that. He took up till age, I don't know, but the data wasn't specific like that.
The data wasn't specific. Okay. What about others? That was, yeah, that was good. Others?
I remember now, it was about the life expectancy, right? So like the
Yeah,
other professions went up to 60s or 50s or whatever, but for students it was very low, like around 18 or something. So
it
that
is
was
20 point
because,
down.
yeah, so it was because like most of the people who died during that age, they were students. It's not exactly, it was like the other way around or something.
Yeah. So what happened was he wanted to study something else. He wanted to study, how much on an average each profession makes a person live for. I mean, that was his goal probably, right? Because the other way around, it doesn't make any sense. But what he ended up doing was he ended up choosing student as a profession in itself, whereas he neglected the fact that even a chocolate maker or even a professor or a locksmith might have been a student once in their lifetime. So he ignored that fact, and what happened was basically the study was all haywire and it just didn't make any sense at all. So again, the concept that underplays here and shines through the weakness of the study is that of conditional distribution. So it's very easier for us to, not act upon the information that we're already given, rather move forward with all that we seem to know and discard the information that is right there in front of us, seeing or seeming that it doesn't affect the chance that we're trying to calculate. So maybe let us try to, do a particular quiz. Not exactly a quiz, but yeah, just a something, just a small little something. So let us say there is a family and they have no children, okay? And what is the probability that the children born now will be a boy? Anyone?
50%.
Okay, so Isha says 50%. So for 50%, I have one vote. What about others?
Same here.
50%.
Okay. Others?
Same.
Anshita says same thing. What about the rest of you guys? I mean, the majority is clearly with 50%. Meher?
Ma'am, can you please repeat the question?
Okay, so the question is that there is no child in a family. So what is the probability that the children born now, that the child born now will be a boy?
Yeah, it will be 50%.
Okay. And I guess Savri, yeah, she's back here. Savri or Anvi, I guess one of you has not voted yet.
And I have.
Okay, thank you, Anvia. Savri, what do you think? 50% or something else? Savri, can you hear us? I think maybe she can't. Okay, so I'll take her vote on that later on. So this was the first. Okay. So now I'm going to ask you guys again another question. So again, as you all said, that there was a 50% chance that the child born would be a boy, and it turned out that it was a boy. So again, now the family has one boy. So what is the probability that the other child will also be a boy?
50%.
Okay, so 2 votes already coming in for 50%.
50%.
Yes,
Isha
ma'am.
says 50%. Here says 50%. This is more interesting, than the America's election. The counting votes. Again, Savri, we
Even
only
I
need
think
your
it
vote.
will be 50.
In both of the cases?
Ma'am, 50.
Okay,
Yes,
thank you
ma'am. I just got the
guys.
question right now, so
Okay, no
I'm
problem.
sorry.
So we have it's all right, it's all right. So we have a majority vote of, 50% for both the questions. So
No
do you guys
competition
see
involved.
no competition? Okay, okay. So if I were to cast my vote, okay, I know I'll be in the minority, but at least in the first question, I'm going to go with 50%. But here, I don't quite agree with 50%. And I'll tell you guys soon why is that not the case. So this is a really interesting example that I always like to, use to show the importance of conditional probability. Okay, so whenever I'm talking about probability, what is the formula for probability? Anyone? Do you guys remember the formula for probability?
Number of successes upon total attempts.
Exactly. That's the number of successes upon total attempts, or number of things that we are looking for upon the total possible outcomes, right? So, okay, let us try to do that for this case. So if I were to derive my probability, what is my sample size consisting of? So if I were to write my sample size, what will it consist of?
A boy and a girl.
Boy and a girl, right? So I have two options, and I'm choosing the probability that the child born will be a boy. So that's going to be a half, right? 50%. Agreed. Let us try the same thing here. So probability that the second child is also a boy, when I have told, so okay, remember the question I said was that one of the child is a boy already. So what is the chance that the second child is also going to be a boy? So now I want the sample size. Can anyone spell out the sample size for this case?
Girl and a boy.
Same as above, right?
It will be boy, girl, and a boy, boy.
You say it will be boy, girl, and a boy, boy. I say you also have to consider girl, boy. So again, because while framing my second question, I didn't use the word, that my first child is a boy. So when I'm saying
The
that
first
there is
option should
one,
not be there, right? The boy, girl should not be there, right?
why?
Because we want the second boy, right?
Yeah.
So then
So
if
these,
the samples,
okay. So what I said was, we have a family wherein one child is a boy, right? So if I'm saying that, there are two childs in particular, then all the sample sizes, boy, 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 girl, boy, and a girl, girl. So if I say that one of them is a boy for sure, then you cancel out this, right? And now your sample size consists only of these three, which are right here.
But ma'am, second child has to be a boy. So then how can it be boy, girl?
So, the way I asked the question right after we discussed this, it was basically to allow you guys to assume that first child was a boy, even though the way I said it wasn't that. So the way I said it was one of the child is a boy, and now we have to figure out, what will be the gender of the second child and what is the probability that it's going to be a boy. So when I say second,
You said that the first child is a boy.
I said that.
Yeah.
Yeah, you did. And also that while assuming the gender of the second child, how can we say that one of the child is a boy? That is after the outcome, right?
Okay. So I never, again, I never said that these two scenarios are going to be connected.
Ma'am, but shouldn't the probability of the second child being a boy or a girl be independent of the first child?
Exactly. I think
That is
that is
what
the
we studied
question.
in negative binomial.
Yeah. I think I think that is what the general convention is as well. But I mean, if you work out in terms of the actual theory that probability is based upon, this is how it plays out. So again, I think if I say the first child, then that is I accept my fault and I'm sorry about that. But again, that shouldn't have to be the case. So the question for this part right here is that if one of the child we know is already a boy, then what is the probability that the second child is also be a boy, is also a boy? So when I'm saying second child, it doesn't mean the child who was born second. It just means the second of, I mean, it could have been third or fourth and not necessarily be the youngest or the eldest. Okay. So what happens is, now if you have a look at it from the probabilistic point of view, the probability that the second child is also going to be a boy is we only have one case here, right? So the probability, if you try to have a look here, will give you the answer 1/3. So it's not always what our intuition says us to do. But again, there is a lot of controversy going on even in the statistic field, because with this particular example, what happens is people do think, that it's not dependent on the first child's gender or the second child's gender, what the other child's gender could be. I mean, it's independent of it. So it shouldn't really be dependent. But again, it depends on the way we frame the question and the thing that we're trying to, look at. So we never, I mean, as a statistician, why would you care about the probability that the child born will be a boy or a girl, right? From the perspective which makes you think that the answer will be 50% for this.
Okay, ma'am. As you said that the probability depends on the way we frame the question. So, can you repeat what was your question over here?
Okay, so in the first case, let's say I'm questioning again. So in the first case, I'm questioning that there is a family that won't have a child yet, and what is the probability that the child born now will be a boy? And in the second case, this is the question that you guys should, think about. So my question goes like this. One of the child born in the family is a boy. What is the chance that the other child or the second child is also a boy? And you can actually, go on and on by increasing the level of difficulty in this question by providing more information. So the another continuation of this can be, there is a family and there is one child who is a boy named Rahul. What is the probability that the other child will also be a boy? And again, it wouldn't be, the same as we would have thought it to be. So again, I think if this sounds really interesting, and if you guys do want to have a discussion about this, I think we can have like a separate session in the next week just for this. Would you guys be interested?
It sounds more controversial and interesting.
I know. So the first time I read this, even I didn't believe it. So I went to my professor and I was like, I'm reading this book and it's written here, and I'm like, I don't know what to do. This author is very famous. This book is also very famous, and I don't quite seem to agree with what's written in there. But as it has been proven, sometimes the so-called Bayesian theorem that we think goes against the intuition of human nature, because we are not tended to think in terms of, Bayesian thinking. I mean, there are two kinds of probabilities that exist. People say that they believe in frequentist, or people say that they believe in Bayesian. So again, in Bayesian, you will have posterior and priori probabilities. I guess you guys might have studied that in credibility theory in CS1. I hope that chapter was interesting to each one of you. But yeah, again, I would say, it's just the way you look at it. So again, if you ask this question to a frequentist person, they will say it's 50%. And that is the majority of the population. But again, there are some people who believe that it should be Bayesian. And I mean, this is what dictates the logic well. So they believe that it should ideally be 1/3. And I don't know, after all of these years, I mean, I'm speaking as if I'm very old, but after 3 years of reading that book, I want to be with the minority somehow. But again, I'll let you guys decide whatever you want to choose. And again, we can have a separate discussion about, this concept. And again, we can do it with the name Rahul as well. And then they'll tell you, Rahul lives in this city, and then what will happen? And then again, the probability is going to change. And it just blows your mind away how so many possibilities exist, and how just by providing you with some information that might seem irrelevant at first might actually, boil your sample size down or increase your sample size to much more than what you seem to think it is. So that is how randomness actually fools us, and conditional probability is actually a lot bewildering. And yeah, I mean, it's good. I mean, I cannot do anything about it, but fall prey to it always without even knowing about it. And I guess that is what makes statistics even more amusing to me. But yeah, I think that's a topic for another day. I just wanted to introduce this to you guys, to get your minds open about some possibilities that, you might never think could exist. So again,
it might
now,
be after including all the biological, economical, geographical, all of those
no,
factors.
they don't do any biological. I mean, you don't need to know any chromosomes and all those stuff. X, Y, Y, Z, no need to know all of that stuff. It's purely statistics. And yeah, so it was actually from a book called The Drunkard's Walk. I don't remember the author, but yeah, I guess. I don't remember the author. Yeah, but it's a very nice book, The Drunkard's Walk. Whenever someone used to ask me while I was reading that book, what book are you reading right now? I used to say Devde Ki Chaal because that would attract their attention, and then they would be, oh, usme kya hota hai? And basically, have you guys heard of random walk? Random walk, anyone? So again, that we will be studying actually that for the next section in our CS2, which will be much more about random walk and stochastic processes. And it is really fascinating. And I think it's a very interesting topic. And that is where we will study about the drunkard's walk. So basically how a drunk person will, walk without even knowing where he is walking, or even if he is walking or not. So yeah, I think it's just very, I shouldn't get, swayed away, because I'm still, saving some of it for the time I literally explain you guys what a stochastic process is. So again, let us start off with, why did I have this talk about conditional distribution? Because in this loss distributions and reinsurance perspective, whenever I'm talking about the reinsurance company, either they can know all of the claims that have occurred, so including the ones that they have to chip in and including the ones that they have nothing to do with. And the other kind of thing that can be there is that they only come to know about the claims that have something to do with them, that have some business to do with them. Otherwise, the insurance company, the ceding company won't even tell the reinsurance company that this sort of a claim has occurred. What they do is they only give the reinsurers the information that is needed for them and nothing else. So again, that calls in for conditional distribution. And the way now we are going to do the sums is we'll define a different random variable for the reinsurer's distribution. So again, you would have to be mindful of what is the question asking you. Does the question assume that the reinsurance company knows of all the claims, or does it assume that the reinsurance company only knows of the claims that they have, to deal with? So again, now I think you guys must have heard the word truncated. Have you guys heard this term before? Yes. Right. So what I will say here now is that the reinsurer is observing claims from a truncated distribution. So they only have a record of the claims which are greater than M. So I'm talking about the non-proportional case here. And if it's less than M, they will not even know if the claim has occurred or not. So let me just try the heading. I've written the spelling wrong. It's an E, right? Yeah. So let us define the random variable as W. And again, if I were to write it in terms of conditional probability, how do you guys think I should be writing the claim amount that the reinsurer will have to, incur? Anyone? So what will I be conditioning upon? What should be the condition? So again, I know there will be something here and something else there. So what should I be conditioning upon for the reinsurer's claim? Exactly. My X is greater than M. Thank you very much. And what should be the claim incurred by the reinsurance company if X is greater than M?
X minus M.
Exactly. It will be the same, right? It is still going to be X minus M, given that X is greater than M. So what we will do here now is we will just, for convenience sake, I'll just write it as Z. So I can write this as Z given that Z is greater than 0, because I can rewrite this as X minus M greater than M minus M, which boils down to X minus M greater than 0. And if I'm defining my X minus M as Z, my W can just be Z given that Z is greater than 0. So we'll see where do I use that. But before I do that, we don't yet know how do the claims of reinsurance company function or behave when we're looking at its conditional distribution. So we'll have to determine its PDF. So we will be deriving the conditional distribution of the reinsurer's claims. So let us try to do that. It's a very hefty task that we have taken upon ourselves, but I'm hoping that we all can, muster enough courage and try to derive a PDF by ourselves. So if I'm writing a capital W here, I will write a small w there, just to represent, the value that this random variable takes at a single point of time. So again, I want to derive a PDF. So what should I write there? Anyone? What do I know about W? What do I know about my random variable W?
will it be probability of z given that z is greater than 0?
Exactly. So again, just ignore the z. And what I'm going to do is I'm going to actually write what z is. So I'll write z as x minus m. Given that, so again, before I write given that, this x minus m right here is just my random variable w. So I have to write that this is lesser than w, given that x is greater than m. Does this make sense?
Yes.
And what do you guys think I should be doing next? So basically what I'm trying to derive. Yeah, go on, sorry.
Will it be probability x minus m is less than w upon probability x is greater than m?
Okay. And why do you think this should be the case? Yes.
Then that's the conditional probability. Then I mean.
Okay. Let us try to have a look at conditional probability with some another sense. So let us say, ignore all of this stuff that we have yet done. So let us say I have some probability that my random variable x is less than a, given that my random variable x is greater than b. Okay, so this is what I'm looking at right now. And this will be equal to what is what we're concerned with in generally. Generally, we're concerned with that. But here, my random variable is x minus m. And here I have x, which is greater than m. And again, I know the distribution function that my x follows. So I know my f of x. And I'm trying to figure out the distribution for my w. And this is what I have to figure out. This is known to us. So
ma'am, can you just go through the red part thing again? I'd gotten disconnected.
This?
Yeah. Like whatever
Okay,
you wrote after w equal to x minus m given x greater than m.
Okay, yeah, sure, no worries. Would anyone want to explain it to her? Or should I just do it again? Would anyone want to volunteer? I'd be very happy if someone can. So, okay, we had W, which is what is the reinsurer's conditional distribution random variable. That is our most prior concern right now. And we have written it as x minus m, given that x is greater than m. So now what I did was I just defined z as x minus m. I mean, I defined x minus m as z. And because I defined x minus m as z, and I can rewrite this as, by subtracting m on both the sides like this. So I can again substitute z in place of x minus m so that I can get z greater than 0. And that is just something that I will use at the very end of this lecture. But yeah, just ignore that fact for now. And then what we were trying to do is we are trying to now determine the distribution function. So basically, how are the claims distributed for the reinsurance company? If we know that they only know about the claims which are in value greater than m or have something to do with them. So again, we try to write, probability that our random variable w takes the value less than some w, which is just, the placeholder value for this. And we substituted the value for w from here up until there, and we just wrote the given thing as it is. And now we are trying to figure out what should we do next. So this is just one of the plausible solutions that Anvaya think should happen. So we are trying to figure out, if this makes sense or not, or if this makes sense, what can we do next?
Ma'am, in the numerator, it should be probability of x minus m less than w intersection x greater than m, right?
Yeah, okay. That makes sense. And where? What do you have to say to that?
Then why is it intersection over there?
Savri, can you explain her? Why do you think intersection should be there?
Ma'am, that's the formula for conditional distribution, right?
Okay. Do you have any other explanation other than, that's the formula for the conditional distribution?
I can't think of any logic right now behind that. Sorry.
It's okay. You guys don't have to be sorry at all. I mean, you guys are here to learn, and my job is to teach you basically. So yeah, I should be sorry that you don't know this yet. Don't worry about that. Mihir, Vanshita, do you guys know why should there be an intersection or why shouldn't there be an intersection here? Which side are you on? Do you support Biden or do you support Trump?
There should be an intersection.
There should be an
Again,
intersection.
same reason, the formula.
And why do you think there is an intersection required?
It's in the formula, ma'am.
I don't want to hear this, it's in the formula. Like, why? That's never the answer you give to a question why. It's because it's written in the book. Yeah, but why is it written in the book the way it is written in the book?
So if it is given that x is greater than m, so while considering the probability, you have to consider that x is greater than m. So for that, the intersection comes in play.
You said a very okay. I see what you were trying to do there. Okay, let me try to maybe do something. So again, I did write this here. Let us try to derive this. Let us say the Bayesian theorem hasn't yet been, invented or discovered, and we don't know what to do about it. So we put ourselves in Bayes' shoes, and let us be the one who is going to now derive, why is Bayesian conditional probability formula the way it is. Okay, so we have something like this. Can someone say me or tell me how many events are we looking at in this expression right here? How many events we have?
Number of
How many events?
2.
2. Who was that? Vanshita, was that you? Sorry. Okay, so Vanshita thinks there are 2 events and she's absolutely correct. So one of the event is that my x is less than a, and another event is that my x is greater than b. Okay, so now what I am trying to do is determine this probability, right? So again, I know that my x for sure is greater than b. So I know for a fact that my x is greater than b, right? So I can safely ignore this part and I'm caring only about this part. So again, whenever I define my probability, what is it? It is the total number of possible outcomes in the denominator and the outcomes that correspond to the thing that we care about in the numerator, right? So again, now what we are asking ourselves is, given that I know for sure that my x has taken a value greater than b, what is the chance that my x will also be less than a? So what do you guys think I should, shade here in the graph to represent this exact probability. The intersection, right? Because that is the only region where my x is less than a and also simultaneously greater than b. So again, this is the part that should be in the numerator, the pink part, and the green part should be in the denominator because that is our samples. That is our sample that we are taking something from, right? Because we have to act upon the information that we were given. And that is why it is the way it is. I mean, that is why you have the intersection, right? Because the way you write this region right here is how you will say that, you know, probability x less than a intersection x greater than b upon the green part, which is the probability that your x is greater than b. Simple, right? You never have to remember the formula ever again. Does this make sense?
Yes, ma'am.
Yes, ma'am.
Perfect, perfect. So again, you know, remember, we are looking at two events here. And again, just to remind ourselves of the case that we are concerned about right now is this. So what are the two events in this case?
X minus m less than w and x greater than.
Exactly. So we have that our x minus m is less than w, and we have for a fact that our x is greater than m. Okay. So we know something about the PDF of x, that is f of x. What do we know about this guy? Anyone? Do we know anything about x minus m? Do we or do we not?
It's possible.
Yeah.
We just know that it's greater than 0.
We just know that it's greater than 0. Okay. Okay, yes. Anything else?
I think we
Something
know
about
that x minus m is reinsurance, that PDF that we derived there. X minus m in the case when we write x is greater than m.
do you mean this? Do you mean this case? Or something else? Yes, Mahir?
Ma'am, when we wrote about the random variable z in case of reinsurance companies,
Yes.
at that time we wrote that x, when x is greater than m, its value is x minus m.
Okay, yeah, yeah. So apart from that, like, do we know the f of x minus m? Because if we are to figure out the probability that this and this happens simultaneously, we need to know, right, you know, something about this and this as well. These two
We
random
will use same
variables, right?
f of x only, right?
Why? Why can I use the same f of x?
Because we have represented w in terms of x.
No, but I have written W in terms of X minus M, right? I do have X here, but I have X minus M here as well.
But ma'am, M will be a constant, right?
Who was that? Savri, was that you?
Yes, ma'am.
Pat your back. That was a very good point. So we know that, M is just a constant. So if I say that my f of x is, let's say, A, I know for a fact that my f of x minus M will be what? Anyone? Can I say something about f of x minus M if I know something about f of x?
It will be A minus M.
It will be
A minus M.
A minus M. Does everyone agree with what Vanshika just said?
Yes.
What about others?
And how come it's M?
M. Which M are you talking about? This minus M?
Yes, ma'am.
Ask Vanshita. Vanshita, why do you think it should be A minus M?
Because the function would not, like taking the function would not create any difference on M.
Let us see. Let us see. So let us say, I'm looking at my f of 3. Okay. And I've defined my M as 1. So my f of 3's value is, let's say, 0.05. And I've already defined everything. My f of 1 is 0.02. My f of 2 is 0.4, and so on. Anything that I want to. So if I have my f of 3 as 0.05, then can I write that my f of 3 minus 1 will be 0.05 minus 1?
No.
Doesn't make any sense, right? Okay. So now we know that we can't do this. So what can I do? Because we want f of x minus m, right? We only know information about f of x. So we only have two options. Either we do something here to make x the subject variable, or we figure out what f of x minus m is. What do you guys think is an easy option?
The first one maybe.
I couldn't hear you, Vanshika.
The first one maybe.
The first one. And how do you think I can go about, carrying the first one? What should I do?
It's just that we couldn't figure out the second one. That's the reason I said the first one.
Okay. I see what you did there. What about others?
I think the first one only. You can write x less than m plus w and then find out the intersection between two.
Pat yourself twice on the back. That is exactly correct. So again, the way I can write and so the way I will rewrite this will make my life way much easier now. So what I'm going to do is I'll just erase this m from here because I know that it is just a constant, and I'll take it on the other side. Oops. So what I will write is that my x is less than w plus m. And then again, all of this thing makes sense because now I have something about x and I can use that, right? Because I'm saying that my x should be less than w plus m, and here I'm saying that my x should be greater than m upon the probability that my x is higher than m. So again, what can I do next? That is absolutely and exactly what we are supposed to do. Yeah. So, okay, what should we do next? So let me just rewrite this expression. I can rewrite this as keeping x in there and filling in these inequalities. So my x should be less than w plus m, and it should be higher than m upon the probability that my x is greater than m. So again, the information I know about x is f of x and capital F of x. So if I were to use f of x and this f of x to rewrite this expression, how do you guys think I can do that?
So using the capital F of x, it will be like f of can we say w plus m?
Yes.
Yeah, so w plus m minus f of m
Exactly.
upon f of m. Sorry, 1
Is
minus
this
f of m.
Exactly, this will be 1 minus f of m. That is absolutely correct. And again, so now what I will do is, instead of writing everything in terms of capital F, I can also, just, this is absolutely correct. But again, just to provide you guys with another form of how you can write this numerator right here is something like this. So let's say if I just, take this numerator somewhere here. So I can also write this as integration of m till w plus m f of x dx, right? So again, that can be one of the intermediate steps, and then we would go to this. But again, this is absolutely correct and does make all of sense. So again, we have this, and now that is our PDF. Is this the PDF of Reinsurer's conditional claim distribution? Can I say that this is the PDF? Yes or no? Did someone say something? I couldn't really hear.
It would be the PDF.
It would be the PDF. That is what you say?
CDF.
CDF, yes. Because why? I'm looking at less than probability. So this would be my G of W, not small g of W. Okay. But yeah, again, we are somewhere. So now let us try to write the PDF. And what should I do if I want to write the PDF?
Derivative.
Derivative, and how will I take the derivative here? Can you help me do that? Again, what will I take the derivative with respect to?
W.
W, exactly. So I'll have to differentiate with respect to W. And then what should I be doing? So what will I get? Anyone? If I differentiate this guy, what will I get here?
The U by V rule we have to use, right?
U by V rule. And why do you think we have to use U by V rule?
Oh, no. Okay, so we don't have any W function in the denominator.
Exactly right. When life is easy, we don't want to make it complicated. So yeah, even I am scared of U by V rule. Like I can never remember the formula of U upon V rule. I get confused, which one do we have to subtract? Like is it the denominator or the numerator that we subtract from? I can never seem to get my head around that. So yeah, I don't prefer that anytime. Let's just do it in simple way if we can. So what do you guys think it can be?
So it will just be d by dw of f of w plus m, right? Like I think that's the simplest way we can write it in right now.
It would be f dash of w plus m upon 1 minus f of m.
So this denominator, we can't forget this denominator as well, Isha. So when you
Yeah.
ignore
That
this
will
f
be a
of m,
constant.
that was correct. But as Anvaya said, I guess, was that Anvaya?
No, ma'am.
No, it was me, Vanshita.
It was Vanshita. Oh, okay. Thank you, Vanshita. So yeah, that was a great point. So if I take the derivative of this CDF, I'll just get the PDF, right? So I can write it as f of small f of w plus m upon 1 minus capital F of m.
Yeah.
Yeah. Am I with you right then? I just received the call. I'm sorry about that. Can you guys hear me well? Hello? Did I lost you guys? Hello?
Ma'am, you're audible, but the voice is little low.
अभी अच्छा आ रहा है आवाज? Wait, let me check if this is connected. I guess it's better now. Okay, so yeah, so this was what? This was this small f of w plus m, which we get once we differentiate this capital F of w plus m, right? And again, can I rewrite this w plus m as something else that I know? Can I?
F of x.
F of x, right? Because what is x? X random variable is just w plus m. So that's it. I can write this as small f of x as well. So again, I can do that, but I'm not going to do it here because we're going to do, okay, maybe I can just. So this is just the PDF of x, right? And in the denominator, what we have is the probability that my x is greater than m. So do you see what happened just here? We actually don't even have to do anything to get the distribution of this, of reinsurer's conditional claims, because it is nothing but the f of x upon the chance that it is greater than m. So kind of something like Anvaya said initially, when she didn't mention this and she only wrote this. because probability that x is less than w plus m exactly upon probability that x is greater than m. So I mean, that was the correct answer which we were getting to, but just not the right way to get at it. So I hope that's clear. And now again, just for the sake of completeness, I'm going to write here comma w takes a value greater than 0. So that's it. We just derived the PDF of Reinsurer's conditional claims. Now let us try to derive its mean. Are you guys excited? Or is it too much to ask for? So again, if I want to derive a mean, what is my first step usually? What should I do? Anyone?
Integration from 0 to infinity w into f of w, g of w. Sorry.
Exactly right. That is exactly right. So integration from 0 to w. I write a small w here. G of w d w, right? Perfect. So now what should I be doing next? Can I substitute the value of g of w here? Should I substitute the value of g of w? And again, I have dw. Like, what does it mean, dw? Do we know the value of dw?
Ma'am, just a small doubt.
Okay, we can have, yeah,
technical doubt. Can we write f of w instead of g of w?
Yeah. So it doesn't matter what you write, but you just have to be consistent with how you're deriving it. So I have defined this, all of it as g of w. So that is why I am writing it as, g of w here. So if you leave it at that, I think, so if you are writing f, I would suggest, so we generally write this, right? But this does not mean the random variable. The random variable is x here. So if you're writing f, you can write w here and still write x here. So you can differentiate this too by the random variable that this PDF corresponds to. So if you write f subscript w, you can go with f as well. I mean, not a big deal. Yeah, Savri, what were you saying?
Ma'am, the limits for the integration won't it be 0 to infinity?
It will be 0 to infinity. Thank you for, I actually kind of forgot about that. So yeah, it has to be 0 to infinity. Again, why? Because we have defined our w as x minus m, given that x takes a value greater than m, right? And I know that my x spans from 0 to infinity, right? So my w will also span from 0 till infinity, because I know that m is just a constant, right? And this will be 0 at minimum because I'm assuming that my x takes a value greater than or equal to m. So yeah, it should be 0 to infinity. Thank you very much, Sabri. And again, now what I will do is, again, I know a whole lot more about x than about w. And if I can, not go through the pain of deriving the distribution of w to even calculate its mean, it would be such a joy, right? Because I'll be, saved from some nice complicated procedure that I might be mistaken in performing. So let us try to convert all of these things that we have, like w, g of w, and dw into x and m, the constant. So again, how can I rewrite my small w as in terms of x? Anyone?
X minus m.
Exactly. It will be x minus m. And then how can I write my g of w?
f of x upon 1 minus f.
Exactly. So it will be just f of x upon 1 minus f of m from the previous slide. And how can I write my dw now? In terms of dx.
dx only.
Dx? What did he say?
Yes, dx.
Dx. And why do you think it should be dx?
Because we have defined that w is equal to x minus m. So when we differentiate, the value would be dx only.
Right.
Because
So basically what is, yeah. So what is dx and what is dw? dw represents the change in w and dx represents the change in x. So remember, this m is a constant, right? So whatever change I do in w will all be reflected in the corresponding changes in x, right? So my dw will just be equal to dx because my dm is going to be 0. It will never change, right? The change in m, I mean, m is a constant, so it's never going to change. So it's going to be 0 always. So we have dw equal to dx. And that is why we get this right there. Perfect. So, okay. Is there something else that I can do now? I have everything in terms of, x. So again, 1 minus f of m, this is just a constant. So I'll take it outside and I'll rewrite it as, probability that my x takes a value greater than m. And in the numerator, I have this 0 till infinity x minus m f of x dx. Okay. So again, if I were to rewrite this, all of this in terms of z, now how can I do that? Anyone? So if I were to rewrite this in terms of z, how can I do that? So remember, what is my z here? My z is x minus m So again, if I just want to, rewrite all of this in terms of z, what can I do to the denominator first? कुछ तो हेरा फेरी करके आ जाएगा, right? Because this m is just a constant.
It will be
So what can
probability
I
of
do?
z greater than 0. Sorry.
Right? It will just be probability of z greater than 0. Why? Because probability of x greater than m can be rewritten as probability of x minus m greater than 0, which translates to probability of z being greater than 0. Okay, what about the numerator? Can we do something in the numerator? So we have two things to compare now. The first thing that we have is the value that f takes, which is small x, when my random variable is just x, and the value, the same value it takes if my random variable is x minus m. So this is my f of z of x, and this is my f of x, right? So what do you guys think? about these two? Anyone? What do you guys think about these two? So this is random variable x minus m, and this is random variable x. So this is my random variable z basically. So I'm looking if this f of x right here changes its value when it is considered with respect to the random variable z. Because I know that I can write this x minus m as z. And again, we would also have to, do something with this dx right here. So I have dx, and the thing that I care about is dx minus m. And what would that be equal to?
dz.
Dz, right? So this is basically the change in z, right? So if I define my, let's say if I'm defining my z as x minus m, and I want to, do dz, it will be something like this, dz minus dm, let's say. And this dm is again going to be 0. So my dz will be dx. But the only thing that we now have to consider is what's going to happen with these guys here. So all the change in x will be reflected, only in z, because m is again just a constant. So yeah. But what about f of x and f of z? What do you guys think will happen?
Is it just f of x?
What do you mean by f of x? Is it like fx, the random variable small x, or f small x?
No, with random variable x, because if like the m is constant, so if z is varying, it will vary according to x only.
Yeah, exactly right. So again, we have to try to look at what is this f saying to us in words, apart from this notations right here. So what does this f of x say to me? Anyone? In words, what does this mean? Anyone? Come on, I'm just asking you, what does this f of x mean in terms of words? Like, what does it tell me? What is this? What does this small f represent? What is a PDF?
It tells us how the random variable
It tells us how the random variable behaves. Is that what you said? Behaves?
yeah, varies, behaves.
Varies. Yeah, okay, good. What about others? What do you guys think? Anything else to add?
Same, ma'am. It gives different answers for different values of x.
Yeah, it will give you different answers for different values of x. And what will that answer be? Like, what will that be answer for? What is the question that we are trying to ask here? To which this is the answer? Yes, Michelle.
It will give the probability, right, for different values of x.
Exactly. It will be the probability for different values of x. Yes. So, I mean, whenever I'm talking about, PDF, it is a probability density function. And it says us that what is the chance that I will observe the thing that I have written in the bracket, which is just small x here. So it just shows me the probability of observing this small x as the value for this capital X, right? So if I'm talking about this thing right here, it is again trying to just figure out the probability that I will observe this small x if my random variable is x minus m. So will that change? Will the probability of observing small x change? Because what I have is capital X minus m instead of capital X only. So will that constant of minus m affect the probability of observing small x? So again, just to differentiate, this is different than what I wrote in the previous slide. Yes. Yeah, so I guess I wrote something like, f of x minus m. So this is different because this is taking a value x minus m where the random variable could be x or it could be z or it could be anything. So I didn't define my random variable over there. But here I'm keeping this small x as it is and I'm just changing my random variable. So will it in a way affect the chance of observing x?
No.
Oh, it will remain.
And why do you guys think it will remain same?
Because you are keeping the random variable x same, means x is taking same values.
X is taking same values. Okay.
Is it because we have a constant there as n?
Yeah. So yeah, m is a constant, yes, but why does m being a constant does not affect? I mean, that is the reason. So yeah. Okay. So when here is said, that my x takes the same value. So that is not quite the case. Not quite what's happening here. So if you see here, I have my x taking the value small x, and here I have this random variable x minus m taking the value small x. So in this case, the value of my x is basically x plus m. So what I am looking at right now is the chance that my f of x minus m will take this value of small x. So the value of x is not the same, but again, the chance that you will have observed small x with this random variable will remain same if it were this random variable. So what you can do is you can substitute instead of f of x, just f of z as it is. So instead of writing x here, you can write z as well and it wouldn't change a thing. So I can summarize this thing as expectation of z. Do you guys see that?
Can you please repeat it?
Yeah. So what I said was, okay, maybe I should, just write one more step here. So what I'm doing is, I can again write this going from 0 till infinity. And instead of x minus m, I'm writing z instead of f of x. So what will this be? Expectation of z, right? Upon the chance that I observe a value of z greater than 0.
Yes.
Perfect. So again, I am always, confused with this. So what I do write this as is expectation of z upon the chance that my x is greater than. So again, don't be bogged down by, this z and w x. Don't care about all of this as of now. What you need to care about is the intuition of why we are doing the way the things that we are. And whenever it comes to a particular sum that you would be solving, you wouldn't be, writing this z. You would just be solving this integral right here. So this is, just for theory purpose and just to make it more clear as to what's happening in actual. But yeah, in terms of when you're solving the sums, you won't have to essentially write this z and stuff. You would be just solving this right here and here because you will know f of x's value and x minus m, and you will have x times f of x. And okay, we'll be doing a sum similar to this. Do we have a time today? Yes, we do have. So let us do a sum. Let us try to, do something. Okay, before we go to the case where we'll be evaluating reinsurers' conditional claim distribution, let us try to do a case where we have a unconditional one. So basically the case where the reinsurer knows each and every claim that has been incurred. Okay.
Excuse me, ma'am, just a
So,
doubt. Sorry
yeah.
to interrupt. Ma'am, I just wanted to ask, like, while deriving that expected value of W, so if we don't replace it by Z, even that's okay, right? We can directly.
Yeah.
Okay, that's
Absolutely.
okay.
Yeah, it's fine. I mean, you won't see this anywhere else. Yeah, I think that's,
Okay.
I mean, it's given in the book, so I was just bound to cover that. But yeah, you won't see this anywhere else. And I mean, yeah, I mean, so this and this are basically interchangeable, and that is why I highlighted this because this is important. This we can forget.
Okay, ma'am.
Perfect. So, time for an example. Too much of theory we did today. Okay, so again, so I have some examples where I see that my claims follow normal distribution with mean 500 and variance 400. And there is a retention limit of 550. So what I have to do is I have to find the mean amount paid by the reinsurer on all the claims, basically expectation of Z. So how do you guys think I should go about solving this? Yeah.
Ma'am, expected value of Z will be expected value of X minus M, right?
Yes.
So from normal distribution, you can take expected value of X and then directly minus M.
No. Let's do it step by step. What should I be doing now? Yeah, it's very confusing for me, to directly go to the answer. I mean, yeah, let us do it step by step.
Z will be written as X minus M.
Okay.
M is constant, so it will be expected value of X minus M.
And then?
You can take expected value of X from the normal distribution because claim follow normal distribution. And then minus M.
So what will be my expectation of X here?
500.
And what is my M here?
Ma'am, it will be wrong because we have, okay, no, I think it's wrong.
And why do you think it's wrong?
Because we have said that Z should be greater than 0 and your expected value of Z is coming as negative. It will be negative.
Exactly right. So this doesn't quite make sense. Can anyone say why can't we do the way that I have just written on the board? Like, why can't we do it this way? I mean, it does make all sense, right? We should get a nice answer, positive answer at least. Anyone? So again, guys, we have to be mindful of the information that we have. So again here, if I were to write the distribution of Z, so if I were to write the distribution of Z, how would that be? Anyone?
For X less than M, it will be 0, and for X greater than M, it will be X minus M.
So I think, yeah, so what should we do now? So remember, whenever I just wrote my expectation of Z as expectation of X minus 1, what I was implicitly assuming is that all of my claims will always be greater than M, which is not the case, right? Because what I said was that reinsurer has all the information. It has information about all the claims. So it does know that there is a value, be it 0, 1 or 2. But we know that there is a value 0 for the claims value less than or equal to M, right? So we will have to take that information into consideration as well. I mean, 0 has no value in itself, but we will have to, take that thing as well into account. I mean, we can't just write that expectation of Z is, actually you can write this. Actually, you can write, that expectation of Z is expectation of X minus M. Because what's going to happen is Z takes the value 0 elsewhere. So it will eventually, just cancel out by itself. It will nullify. And you will be left with expectation of X minus M. But what I am wondering here again is, why can't you write this expectation of x minus m as this here?
Because expectation of x will be from 0 to infinity, and here it should be from m to infinity.
Exactly. You should pat yourself, like 50 times on your back right now, because this was a very subtle point. Exactly. So again, if I want to write this as expectation of x minus m, so my expectation of x minus m here would be from 0 till infinity for x minus m. But what I get for expectation of z here is that the 0 part would cancel out. But then the x minus m part would only be from m till infinity, right? So let us try to do that. Let us erase all of this and try to write what we now know. So if I were to write my expectation of z, let us, go from step to step. So I'll have from 0 till m, and my m is 550. So my x takes the value 0, and I'll have f of x dx plus integration of starting from m till infinity. And what should I be writing here now? Anyone?
X minus mf of x dx.
Exactly, and x minus m is 550 f of x dx. Okay, and now again we know what is this f of x. This f of x follows normal distribution with mean 500 and variance 400. So again, this will just boil down to 0. So what will happen next? Yeah. So what should I be doing now? Anyone? Come on. What can I do now? Hello? Is everyone awake? Hello?
Yes, yes, we are aware.
Thank you for confirming. Yeah, so what can I do next? Can I do something with f of x? And you guys will have to use your table booklets now.
Is it like in place of f of x, we have to substitute the PDF of normal distribution?
I mean, if you say so, I can do that. I can try that. I don't know what
That
to
would
do.
be
I'm
really
relying on you
complicated,
guys.
right?
Yeah.
That would be really complicated, won't it?
Yeah, I don't know unless I try that. Do you want me to try? Or do you know it's going to be complicated and have you tried it already?
I just thought about it and I think it would be complicated.
Okay, let us see what other crew members think about this. Okay, so Mihir, Savri, and Anvaya, what do you guys think?
Ma'am, even I thought of using the PDF from the table. But again, after she said, even I thought that it might be a bit complicated.
Yeah, even I agree. I mean, yeah, it's gonna be complicated for sure. But is there something else that we can do here?
The other thought was to split the integration.
Yes, we can do that. Why not? Let's do that. So what will I be left with? I'll have integration 550 from infinity. And how should I split it? I'll have x.
X into f of x dx minus integration of 550 to infinity into 550 into f of x of t.
Cool. Nice. So I think this seems a bit easier to solve than this right now.
Yeah, it would be 550 into probability that x is 1 minus probability of x is less than 550.
Exactly. So what does my x follow? So my x is the claim here, right? My x is the claim here. So if I were to write this in terms of something else, I can maybe, for a start, write it as 1 minus probability that my x takes a value less than 550. So what can I do next?
Ma'am, shall we standardize that part, probability x less than 550?
Yes, we should. We should. So how will I standardize it?
Probability z is less than 550 minus 500 upon 400. Like, okay, yeah, 1 minus.
Yeah. So again, don't write z here because we're already using another random variable z here, right? So don't try to use z again here. But yeah, I do appreciate. So let us just try to know some standard normal here. That it is less than
550 minus 500 upon 400. Under root 400.
Exactly. Perfect. All right. And what will I get here? I'll get something like this, 550, 1 minus. So remember, yeah, thank you very much. It is 2.5. Yeah, and I'll get 5 here, right? I will get 5 here. Yes. So 5 is how I represent the CDF because I have less than here. And this 5 would be the way I'll be representing the PDF. And this is, if I put 2 dashes, that is the CDF for normal 0, 1. Okay. What about this guy? What can I do with this guy? And do you guys know how to look up this value in the normal tables?
Yes, ma'am.
Yes, ma'am.
Good. So yeah, I'm relying on those yeses. Okay, good. So again, what should I do about this part here now? So again, my f of x here is normal distribution and this is x and 550 till infinity. So this is in a way, similar to figuring out the mean of normal distribution. Does it look similar?
Yes.
Okay, and do you guys know how to derive? Do you guys know how to derive the mean of normal distribution?
No, ma'am.
Do you guys know any another method of calculating mean other than, just figuring out this integration x f of x by the usual method? No, right? So again, tomorrow we will have a look at how to solve these kind of integrals. And there is a nice formula given in your table booklet. So you guys don't have to worry about its derivation because it is a bit monstrous, I would say. And again, that is not required. So if you open up page number 18 of your table booklets, you will see a formula right there. And that will easily, allow you to solve this kind of things right here. Okay, so I think that's it for today. And tomorrow we will see how to solve for such integrals for two kinds of cases. One where f of x follows normal and another when f of x follows log normal distribution. So those will be two separate cases where we'll have a look at, how to make our life easy. So did you guys understand everything that we did today? So it's very important for you all to, understand the conditional distribution of reinsurance claims. And I think we have covered 90% of the chapter already. The rest of it is just bookkeeping, I would say. Nothing much. Formula डालो, आंसर निकालो, खत्म. दिमाग लगाने का काम नहीं है आगे कुछ. So yeah, I think that was it for today. And again, tomorrow we'll have a class. And then next week, I'm not sure, but I'll try to give one class for sure. And if you guys want to have some other sessions where we are discussing something else, so yeah, I'd be more than happy to have those as well. Does anyone have anything, any question or anything else to ask?
Ma'am, do we have R for this chapter?
Yes, yes. So basically, actually, the chapter that we studied previously is called loss distribution, and the chapter that we did now is called reinsurance. And yes, you will have R for both of them. But again, it's just like a matter of one day or like 2 lectures, I would say, because the risk models chapter. So there are again 2 chapters after this chapter that we are covering right now. And those 4 chapters will form one topic in particular for R. So if you know all of those, then it would make much more sense, to do everything in R together. So topic by topic will go, not chapter by chapter.
Okay.
Yeah, and I guess you can ask, Ravi sir or something else about R. So yeah.
Actually, he told he doesn't know R. I mean, he had told it last time while we were
Yeah,
studying
he doesn't know
CS2.
R, but he's supposed to
Yeah,
like hire someone who knows R. So yeah.
yeah.